area, subtract area. Always subtract areas, never subtract z-scores.
I meant to say area, not z-scores.
Alright guys, let me catch up to you here. Most of you guys at least started number 4. So right in the middle, when I've got z-scores, the mean always becomes what as a z-score?
0.
Because the z-score tells you, what does the z-score tell you? From the mean to the data point. I love it. So I don't know if I've said this yet, but every test from here on out, every test, there will be one question you know ahead of time. I'm going to ask you this question on every test. What does the z-score tell you? Or I might say, what would a z-score of 1.03 tell you? Right? So what would a z-score of 1.03 tell you?
The area.
No, careful. The chart tells me the area. What is that z-score? In fact, the chart only tells me the area if I know it is normal. So what does a z-score of 1.03 tell you no matter what the hell's going on?
How many standard deviations from the mean?
I like it. So it would be, the data point would be 1.03 standard deviations above the mean or away from the mean. I'll take either one. You guys kind of with me? So right there, I wish to God that that meant that all of you would get that question right. But experience has taught me that that is not true. You all know a question on the test. We'll see. Maybe you guys can be the first. And what is it now? 16 years of teaching? Lord, I've been teaching 16 years. Holy shit. So 1.51, this is 0. 1.51, of course, has to be up here. So this area should be decently large, right? I mean, it is. There's no question. So when I look up 1.51, what do you get?
0.9345.
I like 9345. Any? 9345 sounds good. Now, some of you guys are going to understand what I'm about to say. That's really cool. Some of you guys won't. But all I know here are z-scores. If this is any normally distributed thing, men's heights, SAT scores, IQ scores, anything that's normally distributed, and I have a data point that's 1.51 stays away, 93.45% is below it. No matter what. That's the power of changing the z-scores as a standardization. No matter what the normal distribution looked like before, the mean could be 1 billion and the standard deviation 100 million. Or the mean could be 0.0002 with a standard deviation of 0.000013. Who cares? If it's 1.51 steps up, that much data is below. Period. It's crazy. Some of you guys are like, oh, what the hell you just said? As long as you get that number, that's good. You understand the idea? That's even better. All right, so where's the negative 0.44?
To the left of it.
All right, cool. So here's negative get out. Negative 0.44. If I looked at area, this area I want? No. So I hate that I just did that. Point greater than. So when I look up negative 0.44, so I won't do the shortcut. Look up negative 0.44. I get 0.33. Go down. 0.33, so that's going to be the area down here. But I want this area, so that's going to be 0.67. How are we doing so far? Okay, maybe. Now, of course, the shortcut would say look up positive 0.44 and you get that same number. Right? This guy, now I'm working on both sides here. I got negative 3.21. Way down there. Positive 1.98 is going to be up there. The area in the middle. Pretty much from here. If you look up 1.98, you're going to get too much. What do you get when you look up 1.98?
Too little.
No, what do you get when you look up 1.98?
0.9716.
That's the the danger you get when you try to guess what medicine is. What about negative 321? 0.007. I like it. Now, please, dear God, don't just give me those two numbers and stop. There's one question, there should be one answer, one probability answer. So what's the area in the middle? I just take these two areas and subtract. I love it, because this goes too far. If I could just make it stop here, that'd kick ass. Well, I could just subtract this much off, and it will stop right there. So 0.9761 minus 0.0007 is 0.954.
754.
I like it.
So you can use that 0.98
Yeah, be careful. I'm going to say it's real slow, which must mean it's a big note to take. You never subtract z-scores. Because z-scores tell you where you are for your problem. If you subtract them, you have now got a z-score somewhere else that's not related to your problem at all. You subtract areas. You never subtract the z-scores. Yeah.
Like, the z-scores, you only use it when the mean is 0, when the average is 0.
When you change things to z-scores, the mean always becomes 0. Not the mean has to be 0 to start with or anything. It's just that when I change the z-scores, the mean always becomes 0. All right, so what about these freaky ones here? What does this mean? 13th percentile. So this poor little z-score dude, how much below him and how much area is there below those z-score that I want?
13.
13%. That's what that means. The 13th percentile. There's only 13% of z-scores below him, right? So obviously he's got to be where? It's got to be down here. So only 13% there. Be real careful. Be really nice to yourself. I put that up there because I know it's an area. If I put it underneath, it's going to look like a z-score. You're going to look it up as if it's a z-score. That 0.13 is not a z-score. The question says, find the z-score. So I don't know what the hell a z-score is. That's the area. That's the percentage. How do I find a z-score for that? No formula.
You just look.
Look it up.
So normally, I'm going to look up, like the 0.44 we did earlier, I would look up the z-score, and I'd find the area in the middle. Now I know the area, so where are the areas? The areas are in the middle. So if I look up 0.13, what's the closest I can get to 0.13?
0.135.
Looks like 1292. That's the closest, right? This is like 14 away, and this is 8 away. If I say that, are you guys understanding what I'm saying? I know it's 0.008, but it's freaking 8 away, right? And the other one's 14 away? So the 8 away is closer. If you guys wanted to split the difference, I know one person, at least I was talking to, wanted to split the difference. That actually makes some more sense, but I'm not going to force you guys to do that. It's called interpolation. It's even worse if you want to go further. You can make a linear function between the two, because you're not exactly halfway screwed then. So you can take the closest one is 0.1292, and what z-score is that? Negative 1.13. So the z-score that has 13% below it is negative 113. Cool. So what about number 3? What's a little different about number 3?
About 5%.
Yeah, it says 5% above.
So it's in the positive.
So here's the 5% above. This is a chart like areas above or below.
Below.
Areas on the chart, are they above or below?
Below.
Below. I love it. So that's 5% above. How much is below?
95.
95.
So you just
I like it. So then when you look at 0.95, what do you get? So it's definitely got to be positive. It's got to be way the hell up there. It's got to be the top 5%.
put 14645.
So let's see. Now here's the special thing about 95. This is what I was talking about earlier. When it's exactly in the middle of two things. Do you see the little asterisk dude? So if this side would be 1.64. This side would be 1.65. So of course right in the middle is 1.645. So those are the times that I do want the one. When it's right in the middle, you might as well split it in half. Split the difference. So this should be 1.645 for a z-score. Yes, sir.
We have to do, like, the reason why it's 1.645 is because it can't, like, it has to be, because it's 90, they're talking about this, so we don't search for 0.05.
What's the difference between saying there's 5% above something versus there's 95% below it? That's just the way you word it. It doesn't change the situation at all. So that z-score that has 5% is the same z-score that has 95% on the other side. So I just did that because somebody back in time chose to do the z-score chart with areas below. So when I have an area above, I just change it to an area below. It's the same exact situation. Now, of course, you can do the shortcut here. If you look at 0.05, you'll get negative 1.645, but you know it's on that side, so you just take the negative one. So roughly about half of you guys understood what I just said. And again, it's a shortcut. Who cares if you understand that or not really? I mean, if you do, that's nice. If you don't, who cares? You can still, you've got the straightforward way of doing things. But if you look up 0.05, you get the negative of what we just got. Because if this tail is 1.645 with 5%, what's the one over here that's got 5% in it? It's got to be negative 1.6, because this picture is symmetric. Right? That's why the shortcut works. If you don't like it, if you're not sure when to use it, never do. It's sort of like your blinkers in your car. Right? Just say, never use those. The stupid people that change lanes and the blinkers going the other way, and now I sound like an old man. Yeah, it's a big earlier today. Okay. So that's number 2 and 3. When they give you a percentage, we have to do the exact opposite of what we do with a regular problem. I don't have a z-score to look up, but I can look up the area to see what the z-score would have been. So number 4 is our classic problem. They give me a mean. What's the mean?
31.64.
31.64, I like it. I like it, but I can't write. And the standard deviation?
8.27.
8.27, I like it. Cool. So what's the probability? If we pick one student who parks on campus, find the probability that the time they spend per week is less than 27.2 minutes. So where's 27.2 minutes? Good. And I want less than that. Now a lot of you guys are going to, I don't blame you, but a lot of you guys are going to skip the picture. But you're the ones who are going to make simple mistakes. Right? You're not going to make a mistake every time, but it's more likely that you're going to make a simple mistake. You're going to answer me, the answer you might give here would be 80%. If you just drew the picture, you knew it's got to be less than half. It's got to be a small area. So what's the first thing I have to do? Start to look into the other. Get a z-score, I like it. So z equals
X minus
beautiful. Data point minus the mean.
divided by the standard deviation.
Divided by standard deviation, all of it.
Negative 0.54.
Negative 0.54.
4.
4?
4.
Because it comes out to be 5, 3, 6, something like that? Okay.
Look up to these.
Now, do you guys see how this is like, this is one step away from the problems in number 1. They didn't give me a z-score, so I make it a z-score. So when I look up negative 0.4, 54, what do you get?
0.2946.
What do I get? Negative 0.54, 2946?
Yep.
Yep. This area here is 0.2946. Like it. So what does that mean? I like it. So I love it. You're saying the percentage of students at Grossmont who park here that take less than 27.2 minutes a week to find a parking spot, it's 1 hour. And you're saying back there the probability of any student at Grossmont that parks here, it's going to be that. Beautiful. They're both the same thing, right? Percentage, same thing as probability. I love it. So, if you're the EPA, and you know the standard deviation of the approximate amount of the age cars that students are driving, and considering how little money students make. I know I had my 84 Dodge Charger, and I drove that into the ground. and it was emitting all kinds of horrible stuff. So if I knew how many students are roaming around looking for a parking spot, I can guesstimate how much emissions there are, and I can, you see what I'm saying? So then you say, well, this is actually a big problem. We got to do something. Not only the students upset, but also we're just killing ourselves in the ozone, right? You guys kind of with me? I mean, that's a possible thing that EPA can do a study to see how much effect the schools are having on the local atmosphere, right? The pollutants that are going into the sky. More than 56 million. My God, these poor people. It can't happen. And of course, this is all made up. I didn't actually do a survey, so I'll say that right up front. I hope to God there's nobody that's been around for almost an hour looking for a spot. Here's physics. Should be way the hell up there. So of course, again, at first,
Find the z-score.
by the z-score, my data point minus the mean divided by the standard deviation. Point 95. Does that sound all right?
Yeah.
Everybody playing at home? So that's 2.95 there. If I look that up, I'm going to get this area here. So when you look up 2.95, you get 9984. I like it. But obviously, that little bit can't be that. Hope to God that not nearly 99.8% of students are going around for an hour. That would be kind of stupid. That'd be like musical chairs with spots and see how long before the students ride. So what is this here?
-1.
Yeah, 1 minus that. So thankfully it's 0.0016. Right, so about 0.2% of students would take that long, theoretically. And then finally, between 15.5 and 19.5, my mean is 31.64, 15.5 and 19.5. I want the area in between there. So, one mistake I see people make is they'll get a z-score. The z-score they'll get is they'll say 15.5 minus 19.5 divided by 8.27. What's wrong with that? What's z-score based on? The distance from the... So I've got to do two z-scores here. You can't just subtract these two. You understand? It's always got to be in relation to the mean. So I've got to find two z-scores. So one z-score, 15.5 minus this. Negative who what? 1.95, does that sound right?
Yeah.
Alright, so negative 1.95. The other one's going to be the 19.5. Negative 1.47. Oh, no, no. Whoa, stop. Alright, so when you look those two up, negative 1.47, what area do you get? Negative 1.47? I like it. 0.708. And then we look at negative 195. 0.256, I like it. So what's the area in between? What, 0.452?
Yeah.
Coolness. So about 4.5% of the students would be out there for between 15.5 and 19.5 minutes looking for a spot. Right? Now as a student, this would be a really good study to do and to release to people on the first day, or preferably before the first day, so you know how to plan before you come to class. And of course, this whole study would be better if it was broken down by time of day. Does anybody here take an evening class? Like 5, 6?
Parking
What's it like parking there?
everywhere?
I mean, nothing is.
There's no cars.
Exactly. I thought you said there's no. There's plenty of parking there. And Fridays, there's not as many classes, but lazy ass teachers, including myself, that don't teach on Friday. So they,
And
in
lazy
fact,
ass kids too.
it's kind of bad that we have so few classes. We should kind of spread them out, but we've sort of made Fridays the days that we have department meetings and stuff. So not as many classes meet on Fridays. We used to have classes on Saturdays back when we actually had money. Now, what about this last one? This is mixing the two in with raw scores. So from this number 2 and number 3, I can find a z-score that goes for this. Where's the 15th percentile going to be?
Negative.
Way down here, yeah.
15%. Yep.
Go get out of it, Jeff. You're doing exactly what I said not to do. So never put the area down below because they look like z-scores. They're evil. So if you look at 0.15, what score do you get?
0.1482.
Yeah, because the closest you can get 0.15, it sounds sort of like a history test. 1492. Columbus sailed the ocean blue. So what do you get for z-score? Negative 1.04. I like it. So this z-score is negative 1.04, but you don't circle that bad boy off and stop. That would say that somebody finds a parking spot a minute before they started looking for one. I'm going to look for it. I'm there. That sounds nice. But that doesn't make damn sense. Negative 1 minute. A minute before you get to school, you're in a parking spot. What the hell just happened? They can't, sorry, we can't promise you that. So how do I convert that score? That's a z-score. But what do I really want? I want the time. So how do I change that back into a time?
You minus it from the.
Yeah, there's a formula that relates z and x. Now let's be smart about it. Here's one reason why we had to take algebra to get in here. There's not a lot of algebra in this class, but it does show up every now and again. Can you solve that formula for x?
Yeah.
Yeah, the worst part about this, now don't put the values in. We're going to actually make a whole new formula, and this is why you learn how to manipulate letters. This formula really kicks ass when you don't know z and you know everything else, because it's already solved for z. Well, freaking hell, let me just make a formula that's solved for x. So then when I know everything else, I just throw it in there and I'm done. I don't have to solve and solve and solve forever. Let me just make a formula. So what's the worst part about that formula you can kill first? You want to solve for x?
Standard deviation.
Yeah, standard deviation.
Multiply both sides.
So if I multiply both sides by sigma, it'll cancel out
That's standard deviation.
there. So you get z sigma equals x minus the mean. So how do you solve for x? Add the mean. So now I get x equals mu plus z sigma. I think I showed you this before. Can't remember. But remember I told you on every test, is there a question about what the z-score tells you? Right? This actually is a note. I allow formulas on formula sheets, but a lot of you guys know now that you can't have notes and stuff on your formula sheet. But look what this says. A data point is this many standard deviations away from the mean. So you can read this freaking thing in English. If you go this many steps away from the mean, you get to the data point. Right? That's what that thing says. So it's a mathematical sentence. That's silly. So it's just a formula, but you can look at it like a note. So when they ask you what does the z-score tell you, that formula tells you the answer. It's silly. Okay, so more immediately, what do I know that I could throw in here? Yeah, the mean is
31.64.
good. The z-score is
Negative 1.09.
yeah. We just looked that up.
8.2
Standard deviation.
times 8.27.
Good, and that'll be my x.
23.04 around.
What is it?
23.04.
23.04
Yeah.
minutes. I like it. So if it took you that long to find a parking spot then per week, then you would be in the 15th percentile. This is a situation where you want to, it's like golf. You want to have a lower score. Right? You don't want to be in the 90th percentile of time to find a parking spot. Okay. Yes, sir.
When we're trying to find the z-score and they give us the percentile, we have to look right. We don't look here, is it
Exactly. So if you know the area, if you know the percentage that lives in the body, in the middle, z-scores live in the outside. So only look out here when you know for sure you have a z-score you're looking at. Because those are z-scores out there. So you better not be looking out here. It's not a z-score you have, right? Cool. Okay, so anything else from that? Else from that? Okay. All right, so before I forget, there'll be a quiz Wednesday. Chapter 5. And I'll have one problem like the problem from this handout. The one z-score problem. Yeah. All right, so now we got the idea of 6.2 and 6.3 down, and even if you don't quite fully understand everything, you can see how the math involved is not difficult at all. And we have that chart. That's beautiful. I did promise one thing to somebody. Let me do this real quick. We're going to redo a problem on here, but I'll show you how to do it in the calculator. Just remember, the calculator is not work. The calculator is checking your work. So for example, let's do number 4A, number 1. Let's try to redo this one. Let's do that. So if you'll, in your calculator, if you go, remember where the binomial PDF was? Binomial PDF, binomial CDF? Does that sound at all familiar? If you hit second bars, where it says DISTR for distributions, do that. See if you see anything that's useful. Just trying to let this guy warm up. This guy, wake up. So you guys see that? You see anything useful? Yeah, the first one, right? Normal P or C. Pretty much, normal PDF is weird. I don't really ever want a particular value, because any single value on here has an area of what? Any single value has an area, this is a little freaky, but what's the area of a line? 0. The area of a line is 0. Because how wide is it? It's a point wide. And how big is a point? Infinitesimally small. So what's the point of all that crap? PDF is weird. We're going to focus on CDF. Because CDF is this whole idea of area below. Remember, binomial CDF was cumulative area from the end all the way up to the point you put in. So for this first problem, I've got the mean is 31.6. Standard deviation is 8.27. And the data point that I'm interested in is 27.2. Now, quick things. This z-score, when you did this work, did it come out to exactly 0.54? It was like 0.536, wasn't it?
0.368. Or 0.5368.
Oh, thank you. Okay.
Sorry.
So, two things. When you do this in the calculator does not round at all. So when you go to check your work, the table only goes out to 2 places, so it's automatically going to be a little bit off. But I'm okay with that because you actually get some benefit from using that table over a period of time. The calculator is going to give me a much more precise answer, but I'm okay with losing a little precision. This dude's awake. Let's see what this looks like. Calculator will catch up to you. So if you go to second bars to get the distributions. normal CDF. So here's your inputs. Input's going to be from what, comma, to what, comma, mean, comma, x. So it's going to be normal CDF. In this case, it's going to be, here's where things get a little weird. For this problem, I want to go up to 27.2. So where am I coming from?
0.
Yeah, sort of 0. 0 is not bad to use here, but you normally want to use negative 99.9999999. Because theoretically, how far does this go? Forever. So if I say here, from, let me put this to this one. From negative 99.99999 up to 27.2, right? I'm going to stop at 27.2. The mean is 3.64, and the standard deviation 8.27. We got 0.2946. Remember? And the actual answer is like 0.2957. Considering it's an approximation, that's pretty decent. Right? It's not too far off. They both round to 29.5%, almost. We'll go with that. How we doing? Is that cool? So if you wanted to do one like number 2, this one, more than 56 minutes, how do you think you're going to have to do that? This normal CDF goes from 2. So you can't say from something to 56, you have to do 1 minus, but you can actually be smarter about it. I want to go from 56 to no. You kind of with me? Because theoretically, this doesn't end. Theoretically, there's some poor student, once every 500 centuries, there's a student who's driving around for a year. And for great goals, I heard about I don't know, they just have a gas truck come in and fill them up every now and again. They throw food in there for them. Alright, so to do this one, more than 56, I can do second bars, normal. So I want to go from 56 up to what is effectively infinity for us. The mean is still 31.64. Standard deviation is still 8.27. We got, where did we get it? 0.0016. Sweet. All right, can't get much better than that. Oh no. Now, if there's z-scores, here's the nice thing. Like number 1A, less than 1.51. If there's z-scores, here's all you need to put in there. You say negative 9 up to 1.51, and you can stop. If you don't put in a mean and a standard deviation, it assumes you're using z-scores. So I only have to put 2 things in, from to, if I'm dealing with z-scores. You guys with me? Yeah.
So the mean is 0?
The mean for z-scores is always 0. So we got 0.9545.
9345.
And it's 9345. Of course, because we didn't round anything. We just had a z-score given to us, so it's got to be the exact same amount. And again, if you don't understand a damn thing that I do in the calculator, that's fine, actually. Pretty much have to show me the work by hand anyway, but it's nice to know how to kind of check this. Okay, yeah.
So this one I can substitute, then like you know how you use it on the graph, you can use this, or you still want to show where this one.
So what do you think? What did I say earlier?
Show work.
Yeah, does this constitute work?
No.
No. You can argue, my poor little fingers pushed the button. I don't care, it's not work. Work is what we did on the sheet earlier. This is if you want to check your work. So if you don't understand this, I'm okay with that. Because most of us will probably not carry a TI home with us. Just in case you have a probability problem, don't worry. That I know CPR. Okay. So, the little last bit of class here, I want to do this, or at least want to do this, the most colorful handout I've ever freaking created. I don't use this, and then we'll see how much time we have left for a little quick in-class reproduction. This is section 6.4, and let me kind of build up to a little bit. The problems we've been doing, if you look at like the last problem with the parking times, we picked how many people? One person. But in statistics, what do we normally deal with? Well, what do we deal with population, but how do we deal with them? Take samples. So very rarely do I actually have a situation where I want to know probabilities about a single thing. I want to know probabilities about a group of things. So for example, if I wanted to test somebody's claim that they could throw a dart really well, or let me say it this way, they could make quite a few free throws. I want to test a claim that they can make a lot of free throws. If I let that person take one shot, is that really good enough? In a way, you'd say, well, you're going to really put him on to show me that he's able to handle all the whatever. But, who the hell knows? It'd be much better to give him a sample of stuff, right? Take a sample of 30 shots. And then if he makes 28 of them, you're like, no, you missed 2 screws, right? Because you're that much of a hard ass on the one. But you guys kind of with me? So, evidence of something needs to be backed up by a larger sample. If you said one person doesn't like it, that's not evidence of anything. But if you say 98% of the 5,000 people I talked to didn't like it, well, shit, that's something. You kind of with me? So, no, you don't like that. You all right? You're shaking your head like, really? So it had nothing to do with what I just said. Okay. So in section 6.4, what we're going to start doing is looking at samples of things so we can start testing claims about samples of things. So the way it is right now, I can talk about an individual person or individual whatever and test a claim about an individual person, but that's not normally good enough. That's good to get us kind of started. So section 6.4 deals with samples of stuff. Where I want my camera to use the file. So first off, I want to do this quick little. Actually, let me do this. Maybe I will spend a little more time on this. Maybe I'll move my camera. Now, I can't remember now if I used the same example setup for Chebyshev's rule, but you remember when I was God and I made everybody younger and older? I don't know if you guys remember that. Chebyshev thing dealt with the population that looked like that, or sample that looked like that. And Chebyshev is all about if you move things further apart to try to escape, the steps I take get bigger. Remember that? And that's why within 2 standard deviations, there's always going to be at least 75% of the data, so forth. Okay, somebody remember that? So let's go back. We're going back to our alternate universe, Florida, where there's only young people and only old people. There's nobody in the middle. Is this normally distributed?
No.
Hell no, right? It's got 2 parts to it. It's all rocky looking, doesn't look right. But the crazy thing is, I don't care what the distribution starts off looking like. If I take, even if I just take 5 people, let me see. What is this a picture of, by the way? Let me really get down to brass tacks. What is this a picture of? 2 mounds. But how did I create this? What did I do in Florida to make this? These are ages, remember? This is like 40 and whatever. So I went around to people and said,
How old are you?
how old are you? Let me see your ID. Right? And then people showed me their ID for some reason. And then I plotted it. So I said, okay, oh, you're 89? Yes, okay, you're 89. And how old are you? I'm 2. Okay, you're 2. Right? I just plotted little dots. And over time, if I did a large sample, I might end up looking like this. Are you guys with me? So this mean is for individuals. This standard deviation is for individuals, because that's where it came from. If I go around now, instead of talking to one person, if I go talk to 5 people, and I say, what's your average age? I'll give you a minute. Okay, what's your average age? Let them figure it out. And then plot that. What the hell difference is that going to make? So if I take 5 people, how likely is it that I get those 5 people? If I just take it randomly. How likely is it that I get those 5 people? Is that going to happen a lot? That should be very unlikely. What's going to be the most likely thing to happen? Am I going to get only very young people?
No.
I'm going to get only very old people?
No.
Am I going to get these people that are all the same age? What's the most likely thing to happen? Spread out. A mixture of people, right? I'm going to get this person and that person and this person and that person and this person. For example, you with me? How are we doing? So I want to make it really clear. The situation I just did is as likely as this situation was, but it's representative of a situation that's going to be happening more often. Are you with me? I'm not going to pick 5 babies who were just born randomly. No, I'm going to pick some old people, some young people. But no matter what, so what's the average going to be if I do every single group of 5 people I possibly can, and then I average those averages? Okay, this is getting weird. So I go around and I ask 5 people, how old are you? And I get their average age and say, okay, and I keep going. What average should I expect? When I take a group of 5 people, what average would you expect?
40.
You would expect the average of 40. Why? Because that's the freaking average of everybody, right? That's your best guess, is the actual average. And the reason that's your best guess is because that's the one that's going to happen most often. You're going to get close to that most often. So if I actually graph this thing, what's it going to look like? It's going to look like this. Probably something like this. Now we're getting weird. So this 40 now is going to be my peak, because that should happen most often. I should pick some younger people, some older people. On average, they should average each other out, their ages. I'm still going to get, the next likely thing to happen is to get a bunch of people around there, and a bunch of people around there, so I should get little peaks there too. Are you guys kind of with me? Which one of these 2 pictures is more normal? Are either one normal? No. But which one's more normal? This one is. Now, if I keep going, if I go n equals 50, believe it or not, I'm going to end up with a picture that looks like this. I don't care if you don't believe it, because I will. Right? It's been a proven fact. They've attacked it with computers and said, computer, take all the samples of size 50. The computer's like, that's what I'm built for, and it just goes to town. Right? I don't feel like doing that, so screw it. Let the computer do it. And then they plot it, and it comes out to be this. It's crazy. It's crazy. That, of course, is very normal. In fact, the magic number, I want you guys to be really careful. I want to be really careful. Let me make this point right now really super clear. This picture represents individuals. This picture, these pictures here, represents groups of size 5, size 50. You guys with me? So what's this mean? The mean of all these groups is still going to be 40. And in fact, I'm going to call it the mean of all the means. Oh, shit. In fact, remember this, real quick. When you do this in your calculator, see if they have any data. Yes. So if I do calc 1 bar stats, see by the standard deviation, do you see what it says? It doesn't say sigma, it says sigma x. That means it's the standard deviation for individuals. This would be the mean, this is sigma x, this is mu x, the mean for individuals. This would be the mean for samples. But that doesn't change. Just because I take 5 of you instead of 1 of you at a time, is the average age going to change? Hell no, it's the same stupid average age, right? Just because I take 5 at a time, ooh. You guys kind of with me? So the mean won't change, but what do you think happens to the standard deviation? If I want to have an average way the hell out there, what does that mean? I must have randomly selected 50 1-year-olds. How likely is it to do that? If I take 50 people from Florida, it should be very unlikely to get far away from the average. So what happens to the standard deviation? It gets smaller and smaller and smaller. I have to be closer to the real mean. So if I have a real average age in this classroom right now, and I take one person at random, they could be very different from the mean, couldn't they? Of course they could. Pick me. I'm probably very different from the mean. But if I take 10 people and I take their average, it would be much less likely that that average would be far away from the mean. Are you guys with me? That average should be close to the mean, shouldn't it? So that intuitive understanding right there is actually what this picture shows. The more people I pick at a time, the closer the average ages should get to the real average. So the standard deviation does get smaller. So the last thing we'll do, we're not going to have time to do that we'll do that next time. But we're going to do this one, little colorful dude. Alright, section 6.4 is going to freak the hell out of you. I just want to tell you straight up, a lot of you guys are going to be like, I don't think I'll be doing this homework, thank you very much. Just want to let you know that's how you'll feel, but that's not what you want to do. You want to actually do it. So this is the concrete example of the abstract as hell concept I have up there. It's very abstract, but you guys are all nodding here, and at least you're humoring me, but I think a lot of you guys kind of got the idea of this. It should make some kind of sense. This is an attempt to show you a concrete example. So I don't want to use a large-ass population and take all day, because it feels like I've already taken all day. But what I did was, there's numbers 1, 2, 3, 4, and I put them in a hat. So sort of like Florida. All right, so there's 4 people aged 1, 2, 3, and 4. And they're all in this big-ass hat. No, the paper's in the hat. So, obviously, the probability I take any one of these out has got to be 1 out of 4. Probably the thing I put down there, right? So it's a 1/4 chance to get any of these. So if I graph that probability distribution, does it look normal at all? No. Okay. So it's very simple things to understand. Hopefully nothing major going on there. All right? So that's if I take 1 at a time. What if I just take 2 at a time and look at the average of those 2? So what's one thing I could do? And this is without replacement, of course, so none of the probabilities change. You with me? But if I take out 2 things, what could I take out? I could take out a 1, and then I could take 1 out again. So that sample would be the sample 1, 1. What would the average of that sample be? 1. It's crazy, right? The average of 1 and 1 is probably 1. So what I did, and this is pretty much exactly what you're going to do for the homework, but the funny thing is if you look at the examples, they've done a lot of the work for you on the problems I've given you. So looking at the examples is a good idea. But look here. Here's all the possible samples of size 2. Is that cool? You could get a 1 and a 1, or a 1 and then a 2, or a 1 and then a 3, and that's enough. So forth, so forth, so on. So the averages are in yellow here. The average of 1, 1 and 1. The average of 1 and 2 is 1.5. Is that cool? I'll take that as a yes. Go on. Now, up there in the original, if I just took 1 at a time, was there anything that was most likely to happen? No, they're all 1/4 of a chance, right? But here, what's the most likely average to get if I take 2? Take 1 and then take another. 2.5. 2.5. That's the one that happens the most. What's the average of 1, 2, 3, 4? 2.5. Average 1, 2, 3, 4. You get 2.5. Are you with me? So the average of the original stuff is the same as the average of this, which we'll see in a minute. If you average these out, there's equal amounts below 2.5 as there are above 2.5. So the average is going to be 2.5, yeah.
Did you get the average for adding the two numbers and dividing by 2?
I love it. Yes, cool. So there's my sample. That's my sample mean. Now we're going to get the sample mean, add them up, divide by 2 in this case. Cool. That's exactly how I got those numbers that are highlighted. Now, the frequency distribution, the relative frequency distribution, it looks like this. There's only 1 out of 16 that's 1. But there's 4 out of 16 that are 2.5, like you guys told me, right? So if you graph that, what's the immediate way you can describe that picture? Yeah, it looks very normal. It goes up, comes down, looks very normal. Looks a hell of a lot more normal than this did, right? The nice thing about this distribution is that it is symmetric. Obviously, you fold the box on itself, right? So it started off symmetric, so I didn't have to take a huge sample to make it normal. If I had a distribution that looked like this, I might have to go up to 20 or something before it started looking more normal. You guys kind of with me? Here, I only had to take a sample of 2, and it already looks normal. If I took a sample of 3, it will look freaking normal. Now, how many numbers are in the hat? But I could take a sample of 20 here. Because what am I doing? Take one, write it down, put it back. Take one, write it down, put it. I can take a sample size of 20, couldn't I? Cool, I like it, I like it. And if I did that, it would look stupid normal. It would look like really normal. Okay. So real quick, let me show you, let me remind you guys how to do this real quick. This is interesting. If you put in here 1, 2, 3, 4. Get in there. Oops. And then you do stat calc, 1 bar stats. What's the standard deviation of that situation?
0.12.
Good, because what's 1, 2, 3, 4 in this case? What is that? That is my, careful, it's an evil trick sort of. It's very small, but that's my population. That is what I'm choosing from, isn't it? My sample size is 2. My population is really small. It's only 4 things, but who cares? Population could be stupid small because it's just me. Everybody else is dead. I didn't do it. So the mean here is 2.5, and the standard deviation of the individual stuff, 1, 2, 3, 4, is 1.118. I like that. Now, going back to this. Oh, here's this here. Now let's do this. Let's do this. This will be a little bit easier. A little bit quicker. I'm going to take and put in there real quick all these here as a sample. Get in there. All my samples I'm going to put together. So this is my population of possible sample means. So I had one. I had a couple of 1.5s. I'll tell you what. Let me cut to the chase. If I did all that, that's going to take a little too long to just watch me doing that. If I did all that, I would end up with a mean of 2.5, and the standard deviation for those sample means would be 0.791. Now, that makes sense. That's what we said. If I start taking samples of size whatever, it should be more likely that they'd be closer to the mean, less likely they'd be further away from the mean. So the standard deviation did get a little smaller. And actually, there's a little bit of a clue here of exactly how much smaller does it get. It's my old standard deviation divided by the square root of 2. Now, where do you think that 2 came from? Sample size. I love it. So the standard deviation of sample means will be the old standard deviation for individuals divided by the square root of the sample size. So if I took 4 papers, 1, 2, 3, 4, it would be 1.118 divided by square root of 4. So divided by 2. That's exactly how much it shrinks. So I think it made sense to you guys earlier that it does get smaller. It should be less and less likely for a sample to be far away from the mean. So they should be closer and closer to the mean. But this formula tells you exactly how much closer on average. What happens to that standard deviation? Gets smaller exactly this way. Whew. So next time, I have a little exercise we're going to do. Not standing up and jumping around, but we'll start off with a little something that I don't have any control over, so I want to see how it comes out. Statistically, I know what should happen, but we'll see. All right. Quiz, yeah, this Wednesday.